Hello, everyone. My name is Emmanuel Bimpo Manfo from the University of Manchester, United Kingdom, and I'm delighted to welcome you all on behalf of the organizing committee to this test series of the seminars sponsored by the European VLBI network, focusing mainly on high-resolution radio astronomy. Just before we start, I want to highlight a few housekeeping notes for everyone to be aware of. First, everyone will be muted throughout this presentation, but you are all invited to type in your questions you may have for our speaker through the Q&A facility. Please, we will encourage everyone to use the Q&A facility to type in their questions during the presentation, and after we will do well to attend to all these questions. You can send your questions both during and after the presentation. So if the speaker is talking and you have a question, please feel free to type it in the Q&A facility, or you can also wait after the presentation and then you type your question in the Q&A facility. Either way, your questions will be attended to or will be answered after the speaker finished talking. Please try to write your questions clearly and keep them short. We will aim as much as we can to get to as many of your questions. And we apologize in advance if for any reason we are not able to have time to answer your question. Now, I will invite Javier Modon, who is a member of the organizing committee from the IAA, to introduce our speaker for today.
Okay, so our guest speaker today is Benjamin Winkel. Benjamin is a professional radio astronomer who got his PhD at the University of Bonn in 2009. He had a leading role in the Effelsberg-Bonn H1 survey, EPHIS, and in the Hi4Pi survey, which combined EPHIS with Parkes data to create a census of the neutral atomic hydrogen in the Milky Way and its halo. Benjamin has thousands of hours of observing experience with major European radio telescopes, and he's an expert in the field of radio astronomy data processing and calibration. Since a few years, he is also very active in the field of spectrum management, being one of the German delegates in the European Committee on Radio Astronomy Frequencies, CRAF, advocating for protecting radio astronomy from interference caused by anthropogenic sources. Together with his CRAF colleagues, Benjamin participates in meetings and conferences of the International Telecommunication Union and other organizations, where important decisions are being made which could impact astronomers' access to the sky for decades. So you're very welcome to be here, Benjamin, and you may start when you're ready. Thank you for coming.
Thank you very much. I will share my screen so that you can see the slides. So my talk is titled A New Dark Age for Radio Astronomy, ? And I'm going to talk about spectrum management. Before I start, I would like to thank the organizers very much for inviting me. That's a good opportunity to strengthen the link between your spectrum managers and the astronomy science community. And I also would like to mention that I'm presenting here on behalf of CRAF, the Committee on Radio Astronomy Frequencies. So all of this is really a team effort. It's not only things that I do. Okay, to set the scene, let's start with a small motivation. So this is a spectrum that was recently recorded with the Effelsberg telescope, and ignore the baseline, the ugly baseline for a moment. This is inevitable if you have a high bandwidth spectrum. It's basically the frequency dependent bandpass that you see here. But I want you to put your focus on all these features that you see on top of it. For example, these rectangular shaped thing here, it's a digital communication signal from your LTE cell phone network. Astronomers tend to call all of this radio frequency interference, but in fact, you usually don't know if that's really the case. If you are in administration or any other user of the spectrum, that's perfectly legal transmissions. Actually, it's wanted transmissions. You all use your smartphones on a daily basis. So it is a bit odd for other people that astronomers call this stuff radio frequency interference. Now, let me show you another example. This is coming from a spectrum monitoring campaign that was done many years ago by a good colleague of mine, Reinhard Keller at MPIfR. And it's a bit outdated, but it is a very nice, it's a very nice visualization. So that's why I keep showing it. So you see again that you have lots of features here in the domain between 500 megahertz and 3 gigahertz. And this is subject to all sorts of human-made transmissions. You have TV, you have radar, you have all these cell phone related data. And the only thing that are really reserved for radio astronomy are these very tiny green blocks here. This is where radio astronomers are supposed to do their measurements. Now, let's come back to the question of when we can actually talk about radio frequency interference. And any transmission, any active service will have assigned or allocated a certain range of frequencies. This is what we call the in-band transmissions, or the in-band domain. A digital signal will have their carriers there, or a radar will have their pulse bandwidths in this area. And then, because every real device is not perfect, simply because there are no perfect electronics, you will have some kind of leakage, spectral side lobes. If you are close to the in-band signal, we call this out of band. And if you are farther away in frequency, we call it the spurious domain. And spurious features could, for example, be harmonics signals. So at twice or 3 times or even higher integer numbers of the carrier frequency. And imagine that radio astronomy would have an allocated frequency right next to an active transmission. So it would be in the out of band domain. If we then receive some signal from that active service which disturbs us, we could rightfully speak of radio frequency interference. But that's obviously not the case for all those signals that I showed here, because they are usually far away from our frequency, from our own frequencies. So be a bit careful how you phrase your interference features in the future. Now, in my talk, I will have 3 major parts. I will first give you an introduction into spectrum management and what the Committee on Radio Astronomy Frequencies is doing. In the second part, I will explain a little bit how we do compatibility calculations, provide an example also. And finally, I provide a list of the current hot topics. This is, of course, not complete. There is so much going on at the moment that I really had to choose some interesting ones, but you will see. Okay, in the first part, I'll introduce a little bit what spectrum managers are actually doing. So I really like to show this graph. This is the frequency allocations for the United States, but it really looks not much different in other countries. I just like that they published this very interesting looking picture, so I keep showing it. And as you see, it's so crowded and you cannot really see something. We really have to zoom in to understand what's going on. And this is just focusing on some frequencies in L-band between about 1 gigahertz and 1.7 gigahertz. And you see that at many frequencies, you have allocations to many different active services. And in radio astronomy also, first of all, we only have a few blocks here. The yellow part is radio astronomy. And in some cases, we even share with active services. For example, here in the OH frequency at 1610 megahertz, there's also an allocation to the Earth to Space mobile satellite service. So that already shows you that there is definitely a need to coordinate between all these active services and, of course, also between active services and radio astronomy. And for this, the International Telecommunication Union, ITU, was founded about 100 years ago, if not more. And what they do is they keep updating the so-called radio regulations. The radio regulations, for one, have this frequency allocation table, which I just showed you. And obviously, there are also a lot of other articles and rules and definitions that somehow guide administrations through this complex process. The ITU does not only do radio regulations, but they also help people to do compatibility calculations. And there are dozens, if not hundreds, of ITU reports and recommendations that really have very precise algorithms, procedures, recipes on how to perform these calculations. What the ITU does not do is the actual licensing or giving operation permits. So this is what we call assignments in contrast to allocations. So ITU does allocations. It's more like letting the world know that in a certain frequency range, you can expect a certain application. But in order to really use an application, you still need a license in your country. And sometimes you even have to pay big money for this. You probably remember how many billions of euros some countries were making this auctioning of these cell phone frequencies. It's also in national responsibility to submit information to the ITU about their own radio stations which they operate. This is called the filing process. That also includes if you bring into use satellites. Now, very important in the ITU business is the so-called World Radio Communication Conference, the WRC. They happen usually every 3 to 4 years, and these are the only things, the only summits where you actually update the radio regulations. So they are really important, and there are more than, I don't know, 4,000 or so participants. And the WRC takes usually 4 weeks. And the last one was in Dubai in end of 2023. And interestingly, it was happening at the same time as the big climate conference. It was crazy that Dubai could host 2 of these major meetings at the same time. All right. A little bit more information about the ITU and how it works. There are all these radio services, and the allocations are usually in a certain priority. So there are all these primary allocations that take precedence over secondary allocations. Of course, safety of life is always much more important and always has the right to operate. And some additional clauses and recommendations exist in the radio regulations. For example, for the radio astronomy service, we have this footnote 5.149, which basically says that administrations should protect radio astronomy operations in some additional frequency ranges. So not the ones that we have an allocation anyway, but some additional frequency ranges. But this is really only then relevant for national processes, and it provides very limited protection in many countries. I already indicated that radio astronomy has a very low fraction of the total spectrum, and we will also see this later when we compare it with how much spectrum cell phone networks have these days. Another important thing to note is that some administrations granted or established radio quiet zones around their radio telescopes. You find that, for example, around the GBT, but also around the square kilometer array sites. And this is very important for these telescopes, because the radio quiet zones limit the amount of spectrum use around these sites much more than what the radio regulations would do. But of course, this is only relevant on your own sovereign territory. if you have a radio quiet zone, you cannot ask your neighbor countries to protect your site, because they have all the rights in the world to use the primary allocations and the secondary allocations in their own country according to the radio regulations. One of the most important documents in the ITU next to the radio regulations, at least from a radio astronomer's perspective, is the so-called recommendation ITU RA769. It contains the threshold levels, that is the power levels that must not be exceeded in our radio astronomy frequencies. They are derived by taking a typical radio telescope receiver with all the parameters that such a receiver usually has, the noise temperatures, the typical antenna temperatures. And from that, you can derive an RMS noise level that you would achieve after a certain integration time, let's say 2000 seconds. And then the thresholds are defined as 10% of this RMS. So this allows us to also have a statistically clean signal from the sky in our bands. And this is one of the tables in the recommendation. It shows these parameters, antenna temperatures, receiver noise temperature that you typically have at certain frequencies. And then it also shows you how much input power you must at most accept in your receiver. And for example, here at 1400 megahertz, we have minus 205 dB watts. So this is a decibel scale. If you prefer linear units, this is 10 to the minus 20 watts, which is a tiny number. And often engineers from active services think we are a bit crazy if we tell them those numbers. But of course, we all know that we can observe Janskis or even milli and micro Janskis these days. And the Janskis is 10 to the minus 26 watts per square meter and hertz. So you see that it all makes sense, yet those numbers are, of course, extremely low. I don't really have time to go into other recommendations here, but still I want to show the list so that if you're interested or need to search for something, you can come back here and check. The ITU is organized in so-called study groups. So there are study groups for all kinds of different services, satellite services, broadcasting, and also for science services. And then each study group has several subgroups, which they call working parties. And under study group 7, we have the working party 7D, which is for radio astronomy. Then I should also mention that there is a European counterpart. It's like the ITU for Europe in a sense. It's the European Conference of Postal and Telecommunication Administrations, or short CEPT. And they too have many, many different working groups. And for the European coordination, this makes a lot of sense because European countries are relatively small compared to other continents. And as you know, radio waves don't stop at the national borders, so there is a lot of cross-border coordination required. And often the European Union wants to harmonize their radio applications when it comes to cell phone networks, for example, or car radars. Obviously, you want to have the same frequencies all over Europe. But I should say that CEPT is not only European Union, it's more European countries than are in the European Union. Okay, now how does stuff happen? These meetings are, or working groups are, what we call input document driven. So you can't just go there and expect that you can discuss your problems. No, you have to submit documents, otherwise you will be completely ignored. And let's assume for a moment you are a stakeholder and you want to achieve something. For example, you want a new European-wide decision, or you want to publish a new tech report or something. Then before you can even start the work, you have to go to some high-level group in the CPT and make a proposal. And then in the meeting, they will discuss this proposal. And if you can at least get 6 or 7 administrations on board who think that it's worthwhile, they will create what is called a work item. So this is very formalized. There is a certain scope, a deadline, and a title, and a list of what the work item should deliver in the end. And this work item then gets assigned to a working group. This working group could be a satellite group, for example, when it's a satellite topic. And they will also have many, many meetings, and they will start basically an empty, let's say, tech report, and then wait for other third parties or administrations to submit text to be included in this new draft. And in every meeting, the participants will look and discuss at all these input documents. And if they agree on something, it will be included, otherwise it won't. So you have to make sure to get enough administrations to support your proposals. Then at some point, the draft will be more or less finished, and then it goes up again to the high-level group, where a decision is made whether this is acceptable. And if it is, it goes into a so-called public consultation phase, where again, everyone can submit further comments, which then go down into the working group again, into the PC resolution meeting. They will be considered and potentially implemented into the draft, goes up again to the higher level group, and hopefully at some point they will publish the final thing. So you see that this is extremely complex and complicated. So this process is obviously also very formalized. And if you make some procedural mistake, you will be ignored. They are very strict about it, and they have to, because it's otherwise it would not work. You also have to follow this process until the end. If you are lucky and get your content into the draft at the very first meeting, no one stops another stakeholder from proposing to delete it again. So you have to make care that that doesn't happen. Also, you always have to have sufficient support from administrations. The administrations are the only parties in these meetings who can vote. Of course, other industry and science stakeholders can participate and collaborate with the administrations on the documents, but only the administrations have a vote in this. So it's very important that you get support from administrations. And needless to say, the input documents must obviously be of high enough quality to be acceptable, and they should also be correct. And during the meetings, you often have to work overnight if there is the need to find compromises because there are too many conflicting views. This is not always done within the meeting sessions, but often in offline work during the evening or even later. Okay, so this brings me to why we have the Committee on Radio Astronomy Frequencies, the CRAF. I hope I could show you already how complex and how laborative all the spectrum management world is. So it would be way too much for a single observatory or institute to perform the work there. And this is why the CRAF committee was established some 30 years ago, with the aim to use synergy effects and work in Europe as an organization, as a collaboration between spectrum managers to survive in this complex spectrum management world. We have member institutes from all over Europe, which you can see in this map. We are technically hosted by the European Science Foundation. They do the accounting for us. We also have a service contract with JIVE, which is very important for us. They offer a lot of services. We have IRAM and LVS among our member institutes, and there are also several observer members. So the Square Kilometer Array, for example, they are really good friends. We collaborate very closely with the spectrum managers from the SCAO, but we also have ESO and ESA. And just to show you how much work we actually have to do. So this is the number of meetings that we attended. This is from a review in 2022, so the last 2 years are not included yet. You see that we attended more than 50 or 60 meetings per year. And if you count all the meeting days, because a meeting is often more than 1 day, you even get to higher numbers. In 2021, if you add that up, it's basically every workday where we attended a meeting. And obviously, it could not be done by one person alone. You need really a team of people to share the work. Also, we submitted lots of these input documents, which I just explained. So sometimes, of course, the inputs are relatively short, maybe just some comments or corrections to existing text. But often enough, when we provide compatibility calculations or longer regulatory assessments, they can easily have the size of a science paper and also require almost as much work. So we submitted like 40 or 50, even more documents per year. Okay, this brings me to the second part. What are these compatibility calculations that I mentioned several times now? Of course, if you want to somehow coordinate between all these active services, or also an active service and radio astronomy, you need to know the facts. How much power would you actually receive from an active service transmitter? And if you receive that power, would that power be too high for radio astronomers to do their work? Are they above the threshold levels that we have to accept or not? And obviously, all of this can only be done in a constructive and cooperative approach with other stakeholders, because you need to know the technical parameters for all these transmitters, their deployment numbers and antenna patterns. And you only get these if you participate in all these working groups and committees. It's also important that you are willing to establish additional mitigation measures. So perhaps a cell phone base station needs to somehow change their antenna patterns or tilt their antenna a little bit to reduce the power that we receive. On the other hand, radio astronomers also have to do their part by, for example, putting the telescopes into remote areas and not in the middle of a city, or that we apply state-of-the-art radio frequency interference mitigation and stuff. So compatibility calculations are actually very simple when it comes to a recipe. First, you need to figure out how much power is actually transmitted from a service into your direction. So this is really the conducted power and the antenna gain of the transmitter. Then you need to figure out how much of the power is lost on the path between the transmitter and your receiver. And finally, you will have to calculate how much of the power that arrives at your telescope site is really also entering your receiver. So you need to apply the antenna pattern of the radio telescope. And then when you have done all of this, you can compare it with the threshold levels that have to be respected. In the details, of course, this can be quite complex. The path propagation loss is all but simple to calculate. But that is really beyond my presentation today. It would take its own talk. And also, if you have large networks, a cell phone network, for example, there are many, many different possible transmitters, all these smartphones, all these base stations. So it's not sufficient to just take a single transmitter and do the math. No, you have to aggregate everything. You have to sum up the power and then study that. And that can be computationally expensive. And this is why we started many years ago to write our own software. So this is a package for the Python programming language. And it provides a lot of features, which I will highlight in a moment. It's free software. You can download it from the typical package servers for Python. It's on GitHub. It also has a full manual, comes with many tutorial notebooks for Jupyter. And yeah, so what can it do? First of all, it has a very nice feature which allows you to calculate this path propagation loss, which is relevant for the second part here. In this map, this shows an example around the Effelsberg telescope, which is situated here right in the middle. And in every pixel of this map, you color code the attenuation, the propagation loss that you would have between this position in the map and the radio telescope. So you see, the farther you are away from the telescope, the higher the attenuation becomes, or the more power you lose from the transmission. But also, if you put in your terrain data, which is very important for diffraction, you see that mountains or valleys can effectively shield some of the power. So if you are in a valley, you will have much darker areas, which means that you get less power at the telescope. Another thing which I will also have as an example in a few minutes is satellite simulations. We even bought a Flight Radar 24 dataset, all aircraft positions for one day over all of Europe, so that we can check what the typical flight corridors are above our CRAF observatories. We also combine all of this with other GIS datasets. So GIS is Global Information System, and it's really nice that you can find so many public sources these days for land cover, the terrain information, but also from OpenStreetMap you can download the road networks. And we use this for a study with car radars. So we put random cars on this road network and studied if we would have a problem with the new car radars. Okay, I will now go a bit more into details for one example, which is for satellite constellations. I don't have much time to set the scene here, but you have all heard about the problems that these so-called megaconstellations pose on astronomy, not only on radio astronomy, but on all of astronomy. And this is a very nice image that shows you that the number of active satellites in orbit really skyrocketed in the last years. Okay, so when you want to do a simulation along the lines that I explained first, so you have to know the transmitted powers, you have to calculate how much is lost on the path between the transmitter and the receiver, and finally compare this with the threshold. So in order to do that for a satellite constellation, you of course need to know where are all these satellites. And this is a theoretical model of the Starlink constellation. This is not how it looks like today. You see here that the simulation already is a few years old. But for the purpose of explaining how it works, it is not an issue. And in the meantime, Starlink launched more than these 4,400 satellites, as you may know. Now, when you have the satellites positions, you also need to calculate where they are in your local sky. So this is now in azimuth and elevation as seen from an observer at latitude 50 degrees. And the color code here is for the distance to the satellite. So satellites that are close to the zenith are of course much closer to you than when they are close to the horizon. Then how much power actually goes into your receiver? So of course, you have to consider your antenna diagram, your antenna pattern for this. And while the real antenna pattern of a large parabolic dish is quite complicated, at ITU there is a much more simplified model that I plot here. It's in recommendation RA 1631 for the example of a 25-meter dish and 150 megahertz frequency. So in the very center, you just have a Gaussian beam, and then you have a model for the side lobes, which is far from realistic, but for regulatory purposes, it's fine. And then at about 100 degrees, you have what you would call a spillover ring. Now, assume that you observe here at about azimuth 30 and elevation 30, and the red shaded color here shows you the antenna pattern. So you have the highest gain in this direction, but then also you have here this spillover ring. And you don't only consider the satellites that fly through your main beam. No, you also have to sum up all the power that the satellites have in the far side lobes. And while they don't contribute a lot on an individual basis, the pure fact that there are so many of them will increase the total power a bit. And in the bottom here, you can see the instantaneous power that the receiver really picks up from all these satellites. So you see when a satellite crosses closer to the main beam, then you get a peak in here. But sometimes when they only go at a certain distance from your bore side, you will still see an increase in power. Okay, now you have to do this for all positions on sky. So what you basically do is you convolve the satellite sky with your antenna pattern and account also for the different distances to the satellites. And then you get something like this, which is basically a washed out version of the satellites moving over the sky. And you do this for the 2000 seconds. Remember that in our recommendation that defines the threshold levels, I told you that our typical observing time that is assumed in all these compatibility calculations is 2000 seconds. So you do the simulation for 2000 seconds and then you just sum it up, you average. And this allows you to compare with the threshold levels. Now, is that already it? Unfortunately, not quite, because radio astronomers have to accept a certain percentage of data loss. So we have to accept that 2% of all these sky samples are above the threshold. And also you would usually like to do a little bit of error analysis. And for this, you have to repeat these simulations several times in order to account for statistical scatter. And when you do that, you just repeat all of this, I don't know how many times, maybe 50 times or 100 times or even more, depending on how much scatter you usually have. And you see it looks very similar in each of the iterations, but there are some subtle differences, especially here in the lower part. And finally, you can then analyze this. You can create a cumulative probability. So in this plot, you just count the received powers that exceed a certain level here. So at some point, all the powers will reach 100%. And the point where the curve intersects with the RA769 level, which is this one, you can then read the data loss, which is basically the distance from here to here. And likewise, you can also determine how much additional attenuation you would need to move that curve far enough to the left so that the 2% point, the 98th percentile, goes right on top of the threshold level, because then you would just have the 2% data loss. So this is what we call the margin. The margin is negative, you have some violation of the thresholds. If it's positive, you are fine. So positive means that this point here, this 98% point, would be left of the red vertical line. Okay, that was quite an example. And finally, let me quickly go through a few more topics that we are currently looking at. One can easily say that the most frightening of all services is currently the cell phone networks. So they have a huge amount of spectrum, and I show this here. So the red blocks are allocated to cell phone networks in Europe, and all these small pieces down here in the second row is radio astronomy. So if you only count the primary radio astronomy allocations where we really have good protection, that's only the green stuff, so it's even less. You see here that whereas the secondary, there is even an overlap with cell phone allocation nowadays, and we cannot really observe in this part anymore. Just to show you, all these blocks, or most of these blocks, were really only allocated to cell phone networks very recently. So they got plenty of new spectrum in the last 10 years. And unfortunately, at the last WRC in Dubai, they even got this block here at 6.6 gigahertz, which is right on top of our methanol line. And if we cannot somehow organize coordination in Europe now, we will actually lose access to the methanol spectral line. We will not be able to observe it any longer. The problem with cell phone networks is not only that they have so much spectrum, but also they are just huge in numbers, and they use relatively high power. So a cell phone base station uses transmit effectively several kilowatts after the antenna pattern was applied. And that is sufficient that you would need to put the base station at least a few hundred kilometers away from your radio telescope to make it work. If it's closer, and it usually is closer in Europe because it's a small continent, there is no way that you can observe frequencies that are used by cell phone networks. And as if this was not enough, we now will see more and more base stations put on aircraft and satellites, where you don't even have the terrain attenuation anymore, because the base stations may be behind the mountain or so. No, you will have them in the sky where you can see them with your full main beam antenna gain. If you were lucky in the past, if you are a sub-millimeter astronomer, you didn't have to deal with interference a lot. This will change, so you better pay attention in the future. And we have more and more activities at ITU and in CEPT where we do studies for applications above 100 gigahertz. So one example where colleagues invested a lot of time is to do studies with car radars, but we will also have communication links between satellites and some ground stations, or even mobile ground stations. And obviously at high frequencies, all the propagation effects are stronger, so the atmospheric attenuation is stronger, and you lose more power if you have a hill between you and the transmitter. But still, you will be able to see this if you don't coordinate well. One of my favorites is that last year we detected a so-called electromagnetic leakage from satellite constellations. So this is a Starlink satellite, and usually Starlink operates at about 12 gigahertz for their normal transmissions. Here we detected the satellites at 150 megahertz. So this has nothing to do with the transmitter signal, but it's merely the onboard electronics or the propulsion that somehow leaks some electromagnetic radiation. And it was quite a surprise how easy it was to detect this. It's logical that there is some kind of EM leakage because every electronic device has this. But we were prepared to do a much more data analysis and to find the needle in the haystack. But no, it was quite obvious. The thing was really bright. So this is unfortunately not well regulated at the moment. ITU really doesn't care only about the allocated transmissions and not about all this leakage. So it's something that we are now trying to find better regulation for. And it's not easy to do that because there's not really an organization that is responsible for this. So we have to do a bit more studies here, how to do that. One thing that is very nice is that we could protect our observatories from wind farms. For wind farms, you have a similar situation as for the electromagnetic leakage. Wind farms are not transmitters. They don't transmit on purpose, so they are not subject to ITU regulation. So we were really happy that we had so many European administrations who still were willing to protect us from wind farms. And again, we did calculations. You can even find a report of the CEPT where we explain how these calculations could be done and what kind of typical coordination zone you would need. This was also handled very well at the Lofer core, where a wind farm was placed quite close to the core station. And so far, I believe that everything worked out very nicely. And this was only possible because the operator of the wind farm was also cooperative and established better shielding to their turbines. Extremely important is also Geodetic VLBI. As you know, they use radio telescopes and VLBI to measure Earth's rotation axis parameters, among others. The fun fact here is that the data they provide is absolutely critical also for satellites. Without the Earth's rotation parameters, no satellite would be able to be in orbit. But yet, if you ask the satellite operators if they would like to protect radio astronomy or geodetic VLBI observations, they usually don't want to hear that. It's a bit funny. And I think we have to do a better job to explain to people why that is so critical. I told you before that the International VLBI Service is also a member of CRAF, so we have lots of colleagues, some of them are even here among the participants today, who are involved with this. And they did an excellent job at the ITU to produce a new report. And we are now also even working on a recommendation, and perhaps we can even achieve more at one of the future WRCs. So this will be very important to protect the new VGOS system in the GeoVLBI service. Okay, I will also have an outlook, but let me first summarize this. I think I could show you that spectrum management is indeed very complex. At the moment, one could say that cell phone networks and satellite constellations are probably the most problematic issues that we have because they are so ubiquitous. CRAF is fighting for your spectrum. However, the pressure on the radio spectrum is really dramatically increasing. So the workload that we have is increasing a lot. The commercial interest is increasing a lot. And that's why we really have to put more effort into this. If you compare how much money we spend on things like new facilities, the resources that we invest into protecting our frequencies is tiny, and I don't believe that that can stay like this. Otherwise, if we lose our spectrum, it will be lost for decades, and there's really no easy way to get it back. As CRAF, we also have the problem that we don't have access to the highest political levels, and in some cases you need that. We are well connected to all the spectrum management organizations, but not all decisions are made by the spectrum agencies. Often, especially when it comes to cell phones, you also have political interests. And I mean, we all want cell phone coverage everywhere. That's understandable. So there is a lot of pressure also from the public to improve the networks, which has consequences for radio astronomy, of course. So the science community as a whole really needs to act. By the way, if you want to keep new updates and stuff, follow us on LinkedIn if you like. And finally, let me quickly finish this with an outlook. So at the last WRC in Dubai, we were surprisingly very successful in establishing new scientific topics for the upcoming WRC 27, which will happen in 4 years from now. There are 2 topics about radio astronomy and satellite constellations. We will have an agenda item about space weather sensors, which is also relevant for LOFA and similar observatories. And we will also study communication networks on the moon, which are needed for science projects. So this will all be very interesting, but also be a lot of work. And my colleagues and I are quite frightened on how much work there will actually be. I also would like to mention the IAU CPS, the Center for the Protection of the Dark and White Skies from Satellite Constellation Interference, which was established some time ago. This aims to protect our dark and quiet sky. So not only for radio astronomy, but also for optical astronomy. And if you want to know more, you should really check out their website. Get involved. It's extremely important to do that. And just recently, they published a first position paper, which was led by our good colleague Gyula Józsa from MPIfR, who's also a CRAF member. At the United Nations Committee of the Peaceful Uses of Outer Space, we also now achieved to get an agenda item. I should not say we, it's not CRAF that was doing this, but it was really the IAU, the European Astronomical Society, and we helped a little bit, but it was really up there, the work of the IAU CPS people who made a difference there. And that was quite difficult to achieve. And finally, I would like to briefly mention that at the next General Assembly of the IAU, there will also be a focus meeting on the future of radio astronomy and which frequencies our community would actually prioritize in the future. So I don't have time to go into too much detail, but so perhaps check out the website. And with this, I would like to finish here. I'm sorry for taking a bit too long.
Yeah. Well, thank you very much, Benjamin, for such a wonderful talk and giving us all the details about the work that CRAF is doing to preserve the radio astronomy skies for us and for future generations. We have time for just 1 or 2 questions. So there's a question from YouTube, and it's actually from Paco. And Paco wants to know, Paco says, thanks, Benjamin and CRAF, for this excellent work. As for Geodetic VLBI, which is the impact, since the interference signals are not usually spatially correlated. So I think Paco wants to know what the impact is, since the signals are not spatially correlated when it comes to geodetic VLBI. Yeah.
It's quite a difficult question. So first of all, when it comes to interference, of course, if you have a network such as VLBI, where the individual stations are separated by very large baselines, interference is usually not correlated. That could be slightly different for satellites, of course, but it's usually not correlated. So people can argue that it will somehow be correlated out. However, if you have a very strong signal, let's say a cell phone carrier, that of course produces a much higher noise temperature in your receiver. So it really reduces your sensitivity. It's like making your receiver less sensitive in a sense. So, and obviously, it really depends a lot on the actual numbers. It's hard to give a general answer to this. It depends on the details.
Yeah. Okay. Thanks, Benjamin. And there's another question here from our participants online. And this is from Pedro. Pedro says, I was in IAU-sponsored Opticon RadioNet experimental committee to work on these topics, that is radio and optical interference. Head was Josiah, your colleague, I think. For months now, I have not heard from this any longer. Do you know what happened? We were also supposed to reach higher people trying to make awareness on this issue.
No, I don't know. I assume that they will soon meet again, so it's not that or something. They were definitely involved in a lot of other stuff in the last months. As I told you, the WRC was happening. And then they worked on this position paper of the IAU CPS. So I assume that they will start with meetings soon.
All right, thank you. I think that is it from our online participants. But just before we go, I have one quick question myself. So, yeah, Benjamin, based on the work that CRAF is doing and what the overview you have given us, do you think space VLBI is probably the way to go, like in terms of overcoming all of these radio spectrum that has been hijacked by mobile telecommunication companies on the planet?
So I don't know too much about space VLBI, to be honest. Of course, when we complain in the spectrum management meetings that we have so much interference these days and trouble, some people asked us, why don't you put all your telescopes in orbit or on the moon? And of course, maybe in 100 years that will be the standard. But at the moment, to bring a telescope, 100-meter dish into orbit is not feasible. That's the first answer. It may perhaps be worthwhile to do this with smaller dishes that do VLBI. Could work, why not? On the other hand, also in space, you now have much, much more activities. So you would have to go to quite large orbits before you stop seeing all these satellite constellations that are orbiting in low Earth orbits. You could, of course, also go to the moon. There are plans to have radio astronomy stations there, but that also is extremely tricky when it comes to the management and the logistics. And also on the moon, there are now companies who want to harvest resources, who want to have bases on the moon, all those things. And we are actually putting a lot of effort also into protecting the so-called shielded zone of the moon. So you may know that the part of the moon that is not visible from Earth is protected for radio astronomy. But that was not disputed for many decades because nobody was ever going to be there. But now that people are starting to want to go to the moon, we now are in a situation where we have to fight really, really hard that that zone stays radio quiet. Okay, so that's also some of our activities.
Yeah, thank you very much. And I think we are just, I'll say, on time. And we will thank our speaker, Benjamin Winkel, once again for his time and a very excellent talk for today.
Thanks for having me.
Before concluding, we have a couple of announcements. We will have our next seminar on the 2nd of May, Tuesday, given by Leah Moravito. And she will actually talk about VLBI, but much lower radio frequencies. So mainly what you can do with low-far VLBI on the radio sky. And with that, soon we will reach the EVN Symposium that will take place in September, early September 2024 in Bonn, Germany. And the registration is now actually open. So I hope that many of you will be coming there. And just last one is that we will have 2 training and schools for EVN users. So if you want to observe with the EVN, but you are not used to the network, or you want to know how to be able to submit observations, get data, and analyze it, we are organizing a e-training fully online that is to get you to know what you can do with the EVN and how you can propose for observations. And this will be only one day on the 25th of April. The registration is free, and now you can already go there and see more information in our website. And in end of September, early October, there will be the European Radio Interferometry School, the ERIS 2024, that will take place in Granada, in Spain. And this one will be about data reduction. So not only VLBI, but the full analysis of radio data concerning different radio observatories. So if you want to learn how to deal with radio data, this is a nice place. And also registration is now open. And with this, thank you everyone for participating in the seminar.